Why don't moonlanders keep themselves warm to survive the lunar night? Will Betelgeuse's explosion cause gravitational waves? Is it even theoretically possible to accelerate close to the speed of light? And in our free bonus question on Patreon, what is my dream space mission? Answering all these questions and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I'll gather them up and I'll answer them here. All right, let's get into the questions. Chuck Fimo, when we study galaxies from the JADE survey, are these the most distant from the observable universe, or are they the earliest after the Big Bang? I thought light from the earliest galaxies was out of sight. So the JADE survey is a survey that the James Webb Space Telescope is doing, where they are looking at small sections of the sky and identifying galaxies right at the very beginning of the universe. And these are galaxies that are being seen at a time when the universe was less than 300 million years old, redshift 14-ish. And this is incredible. I mean, the fact that James Webb can just look in one spot and see these kinds of galaxies when the universe was that young is just amazing. And the galaxies themselves are really interesting. They are baby galaxies. They are a fraction of the mass of the galaxies that we see around us today, but they are already looking surprisingly mature. Many have supermassive black holes at their hearts. Most recently, the most distant galaxy, and I forget its exact number, but it was seen with a clear signal of oxygen, which is incredible because oxygen is the kind of molecule that shows up after many generations of stars have lived and died. And yet already 300 million years after the universe had begun, the presence of oxygen was already there. And so the question you're asking is like, are these the oldest galaxies? Are there older galaxies that we can't see? And these are the oldest galaxies that we can see with our current technology. And that if our technology got better, we could probably see slightly earlier galaxies, like maybe to 200 million years after the Big Bang, or maybe 150 million years after the Big Bang, if we had like some super James Webb. But then earlier than that, we would have a really hard time being able to see any more galaxies. And it's not because we can't see that far. And it's not like those galaxies have fallen over the cosmic horizon. It's that early on, the universe was filled with a fog. And not the original fog. Like when you think about the cosmic microwave background radiation, that is the farthest that we can see. And that is 380,000 years after the Big Bang. But then after the cosmic microwave background radiation let all this light into the universe, then the universe cooled down and went dark. That there was no stars had formed yet. And so nothing was illuminating the cosmos. And you got this cosmic fog. And so they call this period the Dark Ages. And then you got this period of reionization when all of the early stars started to heat up the area around them, and then the gas started to glow. And then eventually that gas started to clear out, and finally we could see those first stars and galaxies. And that wasn't much before the galaxies that we can see with James Webb. So no, James Webb can see pretty much right back to the earliest galaxies that is possible for us to see. Now, many of the stuff done with the JADE survey, this was seen directly, but you can imagine future lucky gravitational lenses where James Webb will be able to see some galaxy that's even farther because it's being lensed by a foreground object. And that will be not only the most distant galaxy that we've ever seen, but probably the most distant galaxy that we can see, because earlier than that, everything was obscured by this fog. Silas Miller, what's with these lunar rovers dying of cold? There's got to be some way to generate enough heat to keep a battery alive. Yeah, we've seen that in general, the spacecraft that are sent to the surface of the moon only last for one lunar day, 14 Earth days, before the lunar night kicks in and it kills the spacecraft. And would it be possible to keep a spacecraft alive from day to day, night to night? Absolutely. The Chinese, their Chang'e missions have survived multiple nights. There was some of the Luna missions. There have been missions to the moon in the past that have been able to survive. Japan Slim lander wasn't supposed to survive the lunar night, but it did, and came back like month after month after month, even though it was lying on its side. So it is definitely possible to allow a spacecraft to be able to survive that, but it requires very special engineering. A good example is what you have with, say, Curiosity and Perseverance. They have radioisotope thermoelectric generator on them, an RTG. And this is a chunk of decaying plutonium that is constantly putting out large amounts of heat. They extract that heat into electricity, and they use that both to keep the spacecraft warm, or the rover, as well as provide the electricity for it. And so they're kind of immune to the cold. Spirit and Opportunity had solar panels, and then they would have battery on board, and then they would collect sunlight during the day, and then they would use that to run heaters for the spacecraft at night until the sun came up, and then they were able to warm themselves again. But they also had little pebbles of plutonium, that same stuff that's in the RTGs on Perseverance and Curiosity. They had those little pebbles of plutonium on board that also contributed a little bit of heat to the spacecraft to help it to keep its electronics warm. And the thing that kills it is the battery. So if your battery goes below zero, and definitely if your battery goes 100 degrees below zero, for a long time, it's not going to come back. And so you got to keep that battery warm. Be able to make it through a Martian night is not that hard. It's not that long. You just have to keep the battery temperature just warm enough so that it doesn't suffer any degradation. But on the moon, you've got to be able to have a battery pack that's capable of keeping your spacecraft warm for a long time. So there are a bunch of ideas that you can imagine. Like, one is that you go to a place that's in sunlight all the time. And, there are the permanently shadowed craters on the moon, but there are also mountain peaks that are in large amounts of sunlight, and that you could probably minimize the amount of nighttime that you would have to go through and maximize the amount of daytime that you could enjoy. So that's one possibility. The other possibility is that you can carry an RTG. Like, if you're willing to spend the hundreds of millions of dollars that it would cost to supply a chunk of decaying plutonium, then your heating problems are over. But they're hard to get and require very special agreements with the US Department of Energy, and they don't give a lot. And so, a lot of these spacecraft, they don't have any of this kind of budget. They're done for $60 million, $80 million. Like, these current crop of landers going to the moon are doing this on the cheap. But there are other ideas that have been considered and I really like, which is that you can use the regolith as a way to keep yourself warm. You can imagine, like, one idea is that you could just dig yourself into the regolith. But people have proposed that you could put some kind of, drill a probe down into the regolith, and then while it's daytime, you could be storing heat underground. And then when night comes, then you start to draw that heat that you've stored underground. And we've seen that work really well in places here on Earth, like Finland. They have sand batteries where they store heat underground, and they can be extracting it for months all the way through the winter. And so this is an engineering challenge. And right now, this first crop of spacecraft are not designed to be able to survive that long. They're disposable. But you can imagine future spacecraft are going to be designed to be a more permanent station. The European Space Agency is planning a series of lunar landers. Sort of, they're planning a generic platform that will then hold instruments, and they're designed to last for multiple lunar nights. But like I said, the Chinese are doing it right now, so none of this is impossible. It's just how much money are you willing to spend on your mission? And right now, the lunar lander budgets are less than $100 million. And so you just kind of get what you pay for. All right, it's time to celebrate the $5 patrons that have recently joined us. Thanks to Michael Bade, Carbs, Chris O'Connell, Southpaw, James Geckel, KJDNKQPVNCJCT. Thank you for that. Russ, Daniel Lazan, K1W, and Lord of Entropy. Join the club at patreon.com/universe today. Larry Ward, what's happening with the expansion of the universe? So I'm not sure exactly which news article you are talking about, but there's been a lot of news recently about the role of dark energy in the expansion of the universe. And where this started was this idea of the Hubble tension, that astronomers measured the galaxies nearby and the rate of expansion. They got one number, and then they measured the rate of expansion based on the cosmic microwave background radiation, and they got a different number, and their error bars don't overlap. And so this has led people to consider that there must be some new physics that we don't understand, that maybe we don't understand gravity at the largest scales. Maybe there's a measurement error. Or maybe this additional force that's been discovered, dark energy, has been variable over time. So instead of it being this constant accelerating pressure in the universe, the amount of dark energy that is entering into the universe has been varying, that it was a lot stronger early on in the universe, and then it has lessened over time as there's more universe. And this has been a theory to explain this discrepancy on the expansion rate of the universe, but there hasn't been a lot of evidence because people haven't been able to measure the expansion rate of the universe at different times in its history until now. So there's a bunch of new instruments that have come online. One is called the Dark Energy Spectroscopic Instrument, DESI, which is a ground-based observatory. And they've been measuring the universe back to billions of years ago and then just charting how the universe has been growing over time. But then there's a whole bunch of other experiments coming online. There's the European Space Agency's Euclid mission. There is the Vera Rubin Observatory that's coming online. There's the upcoming Nancy Grace Roman Telescope. There's SphereX. There's a whole bunch of instruments and experiments that are going to be doing this really detailed measurement over the expansion of the universe over time. And DESI is the first out of the gate. And even so, the first results of this seem to support this idea that the influence of dark energy has been decreasing over time. And that's like good news for one apocalyptic way that the universe might end, that people thought, well, if dark energy is increasing over time, then that might eventually tear apart the very structure of reality in the far future. But if dark energy is lessening over time, then the added acceleration from that is, less over time. So we're at very early stages of, there are 6 experiments, all of which are going to be able to participate in our understanding of this. One has delivered their first results. So stay tuned. But I would say within 4 or 5 years, we will have just like a really comprehensive understanding of what the universe has been doing over time. And that may very well lead to brand new physics that will teach us about the expansion of the universe. Lost in space. When Betelgeuse goes boom, will there be detectable gravitational waves? So we have detected gravitational waves from colliding black holes. We've detected them from colliding neutron stars, but that's because you've got large amounts of mass that are moving. The problem with a single star going supernova is that you don't actually have a lot of mass that is moving in this kind of concentrated area. Yeah, you have the thing imploding and then exploding, but it's not like a black hole with 30 times the mass of the sun is spiraling around another black hole with 30 times the mass of the sun, and then they are colliding into one another. You've got this star that's just going, right? And so it's all about the movement of mass. Now, astronomers have proposed that they could detect supernova going off if they are asymmetric. So in other words, if the supernova only part of the supernova detonates and you get a kick in the opposite direction of the star, then you're going to have a mass that moves, or it's going to detonate and spiral or something. Then as long as it moves, that's when you're going to get a detectable gravitational wave. But even that is beyond the capabilities of the current class of observatories. There are more observatories that are in the works, space-based as well as ground-based observatories, but we're just not there yet. Boreum. Do you feel your audience growth has stagnated? I don't think so. The thing that I've noticed is that my audience is very stable now. Like the same group of people show up, or the same number of people show up on a regular basis. And so before we used to get these spikes where we would have one video have 1 million views, then the next video would have 4,000 views. And so clearly it was the algorithm. But at this point, the algorithm has moved on. Yeah, it's into Mr. Beast right now, or I don't know what it's into. And so we're not doing the kinds of things that the algorithm wants. And so we've got more of a baseline audience that shows up on a regular basis. It's a more organic growth. And, it feels like it's a much more vibrant community, that instead of it being one-time people who are watching our videos because the algorithm randomly showed it to them and they don't really have any history with what we do. Now it's people who are regular viewers. I see your names and I recognize you, right? Week after week after week. And I think that the thing that, is really exciting, is now that we're supported 100% by Patreon, is I just don't care. I just don't care. I don't care about algorithms. I don't care about artificial intelligence. I don't care about what the social media companies are doing. I don't care about any of that. Like, all I care about is being the best journalist that I can be, and bringing together a team and leading a team of journalists to report what I think is the most comprehensive news coverage that we can. And everything else now, all of the stuff that I used to have to worry about, is all gone. And every day I just wake up and just go like, what news is important today? What do I, right? That's it. It's so good. So, I think the thing we've all learned when we're creating content online is that the various social media places are your fair weather friends. They're there for you briefly. They love bomb you in the beginning and let you know how great you are, and they want to have meetings with you, and they want to give you representatives who are going to help you with your chart a path, and they're going to recommend the ideal number of times to post, and make you really excited about your content. And then they move on and they're like, oh, we like shorts now. Oh, we like live streams now. Oh, like whatever is the next thing. We're in VR. Like, if you're not making VR, then we're not going to send you any traffic. And it's just not sustainable as a creator. What it causes is burnout. That you can see, there's so many of these we need to talk videos from YouTubers. And generally, the thing that they have to say to you is, I am burnt out. I am destroyed. I can no longer do this work. The algorithm is telling me to go faster and go faster and go faster, and I just keep working and I never take a break, and yet things go down, and then I get more anxious, and so they're depressed and they're anxious and they're overworked, and YouTube has sucked the joy out of them. And they're these dried up husks that then have to go on some kind of spiritual retreat to rejuvenate their joy and love of humanity. And I never feel that, because I was able to early on recognize that it's this toxic feedback loop, and that all I can do is follow my curiosity. All I can do is go, I want to know more about this topic, about this mission, that NIAC project, this new discovery made by such and such mission, and talk to the people involved. And that's what I thrive on. And so it's impossible to make me feel burned out, because I'm having such a good time having these kinds of conversations that I want. And the price that I pay is that the algorithm doesn't like it. That if you go and look at the kinds of videos that we produced, the interviews deeply underperform. Like, they get a quarter of the views that you get from the news, but it's growing and it's stable, and I don't care, because I enjoy doing it. And thanks to the support of the audience, we can just keep doing it. And there's enough people that, when I talk to them, when I talk to the patrons, they're like, oh yeah, the interviews are my favorite part. I'm like, perfect, right? We are of one mind. I like to make the interviews. You like to consume the interviews. Nothing else matters. Oh, Ish Waddup. Is there any way to accelerate to close to the speed of light without emitting radiation and particles and destroying your destination when you stop? Sure. So, for starters, we don't know a lot of ways to be able to get to close to the speed of light. One way is with a laser sail, where you are accelerating your spacecraft from some outside laser. How are you going to decelerate it again when you reach your destination? You're probably just going to do a fly through, but maybe you have a powerful laser at the destination that then fires and decelerates your spacecraft. So you don't have to worry. You're not sending particles at them. The other way is using antimatter, and you are definitely going to be releasing a lot of radioactive particles when you are accelerating due to antimatter, but it's more of a risk for the spacecraft, for the people on the spacecraft, that you've got all this radiation coming from your engine, and that's going to be a problem for the people. If it's a robot, who cares? But if there's people there, then it's a concern. And then, there's not really particles that you're going to be accelerating and dragging along with you and causing damage to the target star or planet. You're going to be decelerating with plenty of time to arrive. You're going to be able to very carefully and slowly go into orbit around your destination, assuming you've got a lot of energy to spare. So I wouldn't worry about it. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call this Q&A Plus. And this week's bonus question is all about my dream space mission. Put a link in the show notes so you can check it out. All right, those are all the questions that we had this week. Thank you everyone for asking them in the YouTube comments, as well as everybody who showed up for the live stream, which we record every Monday evening somewhere in the world. Now the time rotates, and I apologize to do this, but sometimes we do it where it's early evening for North America, sometimes early evening for Europe, sometimes it's early evening for Australasia, and this is to give the world a chance to be able to participate in these live streams, and it rotates and it's hard to know when it's going to happen next. And the best thing is that I will always put an event here on the channel. You can subscribe, notify, and you should get an email from YouTube when it's about to happen, as well as all of the other ways that YouTube will try to let you know. And you know, you can trust YouTube to do that, right? Now, I'm going to talk about another show that I do that we just celebrated our 750th episode. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bodie, Carrotwing, Chuck Hawkins, Commander Baylock, Cy Nelson, David Gilton, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hans Schultz, Hudson Moore, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Modzo, Paul Robach, Ren Kaidu, Robeck, Sean Sargent, Stanislav Zardev, Stephen Fowler-Munley, Thomas Hill Skadron, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. So we just wrapped up recording episode 750 of Astronomy Cast. And for those of you that don't know, this is a long-running podcast that I do with the astronomer, Dr. Pamela Gay. She is the head of CosmoQuest, which is a research group, but also we collaborate on Astronomy Cast. And this has been going since 2007. Our first episode was why we explained that Pluto is no longer a planet. And then each week we pick a different subject, and then we have just a natural conversation about that. And we've done 750 episodes. So we have covered every single possible thing that you can imagine. Gravitational waves, black holes, various planets, and so on. It goes on and on and on. And it's great that we have been doing this for so long. 18 years of doing episodes of Astronomy Cast, and we still have not run out of topics. And so if you wonder why I know a lot about astronomy, I've had personal education from a PhD astronomer for 18 years, and that has definitely helped in my astronomy knowledge. So if you want more content, we do the show live every Monday at 11 Pacific time. And so you can show up for that and ask your questions from me or Pamela. But also it's a podcast that you can find across any of the podcast networks that you listen to. And we've been around forever, and we will be around forever until the heat death of the universe. Or we get our robot bodies, or whatever comes first. All right. We'll see you next time.